So now we will see how we can calculate the deformations in a beam of varying cross section. Suppose there is a beam where this cross sectional area of this portion is A1, cross sectional area of this portion is A2, and cross sectional area of this portion is A3, and the force P is acting, a tensile force P is acting on this. So the length is L1, L2, and L3. So the total deform we have to calculate, we have to find out the total deformations. So total amount of deformation delta. The total deformation or change in length delta will be equal to, we know that for any section the total change in length is equal to PL upon AE. So for this section, so the total deformation will be P into A1, sorry, P into L1 So this will be equal to P L1 upon A1 plus P A1E, P L2 upon A2 plus P L3 upon A3E. So if the section is varying, or similarly, so this is how we can calculate the deformation. Similarly, if the if this is also changing, if this is of material steel, this is aluminium, and this is say brass. So modulus of elasticity here is E1, of this portion is E2, and here it is E3. So now in this case, total deformation will be equal to so in this case the total deformation so when the material is also changing along the length, then total delta will be equal to P into L1 upon A1 E1 plus P L2 upon A2 E2 plus P L3 upon P L3 upon A3 E3. So now let's just take a similar problem. A problem where this 8 kilonewton is acting here. Force. This section cross sectional area is A1, length is L1, this is A2, length is L2, and this is A3, length is L3. 10 kilonewton force is acting here, and 4 kilonewton is acting here. 2 kilonewton force is acting here. Let's name these sections as A, B, C, and D. So similarly, we will draw the free body diagrams like like they were drawn in the previous lecture. So we'll draw the free body diagrams. So the free body diagram of this AB will be, if 8 kilonewton force is acting here and 2 kilonewton is acting here, then for balancing the forces we will add a force of 6 kilonewton here. So the sum will be equal to 8 kilonewton. Now we'll draw a free body diagram for BC. For BC, when if we add this force 6 kilonewton for balancing, then equal opposite force has to be added here, that is 6 kilonewton. Now at section C we have a force of 4 kilonewton in this direction. So 6 plus 4 is 10 kilonewton. So that this we will have to add here. Now the free body diagram of now we have to draw the free body diagram for CD. When we added a 10 kilonewton force here, so for balancing this equal opposite force of 10 kilonewton has to be added here. 10 kilonewton on already, and a force of 10 kilonewton is acting at section D. So now we can see that AB is also in equilibrium, BC is also in equilibrium, CD is also in equilibrium. So the free body diagrams are correct for all these, for this entire beam. Also we can see in the beam the total forces acting towards left are 8 kilonewton plus 4 kilonewton, 12 kilonewton, and total force acting towards right 10 plus 2 is 12 kilonewton. So this entire body is also in equilibrium. Now the deformation for section delta 1 is equals to, for AB, when this length is L1, L2 and L3. So deformation delta 1 will be equal to P with force is equal to 8 P L1 upon A1 E. Delta 2 will be equal to total force acting at a particular section is 6 kilonewton. So net force is 6 kilonewton. P6 into L2 upon A2E. Delta 3 will be equal to net force is 10 kilonewton, 10 into L3 upon A3E. So if we add these three, this will be the total. So total deformation will be equal to delta 1 plus delta 2 plus delta 3, which is equals to 1 upon E, 8 L1 upon A plus 6 L2 upon A, this is A1, A2. and 10 L3 upon A3. Also, if we calculate this according to the principle of superposition, the way we did in the last problem. So in this section in this section A1 of section AB of a cross sectional area A1, we know that the total force acting is 8. So the deformation will be 8 L1 upon A1 E1 or A1 E, because material is same. And for this section, BC, the total force acting will be equal to 8 minus 2 is 6. So it will be 6 L1 upon L2 upon A2E plus, what is section CD, net force is 10. So 10 L3 upon A3E. Right? This is how we can calculate the total deformations or the total strain in a body, if even if the cross sectional area is varying, and also if even if the material is different for different sections and different amount of different forces are acting at different sections. So first of all, we have to draw the free body diagram, and then we have to calculate the forces that are acting on those individual elements, like this element A, B, B, C, C, D. We calculate the total deformation of each element, then we can add up the deformation occurring in each element, so that we can find out the total deformation that has taken place, if that is occurring in a particular body, in the entire being. So suppose we can see that in these three elements, this one A, B, B, C, and C, D, the forces acting are tensile. So the deformation of AB or deformation of BC and deformation of CD, all these deformations are positive. That means the length is increasing. But if any one of the deformation is negative, that means length of is decreasing for any particular element, then we will simply put a minus sign on the deformation. Suppose this deformation delta 2 was negative, then we will simply put a minus sign on this delta 2 and add these three, add the three deformation. That means the total deformation would be delta 1 minus delta 2 plus delta 3. So if the length is increasing, we will say that the deformation is positive, or and if the length is decreasing, you can say that the deformation is negative and add all the three. So this is how we can calculate the total deformations. Now we will also take up a problem on how if different forces are acting, or a problem can be like this. A problem can be like this. If there is a bar and the area is decreasing, the area of this is A1, and area of this portion is A2, and we are applying a force P, then what will be the total deformation in this body? Or the problem can be like this. We have this bar in this, or We know the weight of this body, of this bar. So no force is acting here, but it has got a weight W1, it has got weight W2. So what will be the total deformation due to self weight? So we can have such type of problems that we will discuss. How, what will be the total amount of deformation, or there can be another problem. We can calculate, like for this problem, the total amount of force is P. So the total increase in length will be equal to P into L1 if length, this is length L1, and total length from here to here is L2. So the total deformation delta will be equal to P upon E, or we can say that will be equal to P L1 upon A1E less P L2 upon A2E. Here we are not considering the total weight of this body, self weight of these objects. Or if we are considering the self weight, then we have to draw a free body diagram. If we draw the free body diagram, W2 is acting here, and say W1 is acting here. So for this portion, for balancing, so we can say that W2 is the force here, and for balancing this we have applied a force W2 here. Okay, so now if we have applied a force W2 here, that means we have to apply this, balance this by a force W2 in opposite direction, applied in opposite direction for balancing this section. So now plus here we can see plus W2 is W1 is also acting here. So the net force here will be equal to W1 plus W2. So deformation for this section delta 1 will be equal, delta 2 will be equal to W2 L2 upon A2 E. And deformation for this section will be equal to W1 plus W2, because the total force acting is W1 plus W2. W1 plus W2 L1 upon A1E. So the total deformation in this case will be equal to W1 plus W2 L1 upon A1E1 or A1E plus W2 L2 upon A2E. So this is how we can calculate the total deformations in these type of problems. We will discuss more problems here. We will also discuss some more problems in the coming lectures, in the future lectures.